Hey, so today we're going to do some math on how to find the largest square when you know the area. So I was shopping for deck paint and came across a common problem. When you go to buy paint, they describe the coverage in terms of the area. In this case, square feet. They also include a handy cheat sheet on the side of the paint can. In case it's pretty simple because my deck is also a rectangle. Simple subtraction shows that 75 square feet worth of paint minus 63 square feet worth of deck is about 12 square feet worth of spills and drips before I'm in trouble. When I'm laying out projects in my head though, I like to think in terms of what's the largest square I could make using the area a given amount of material can cover. This gives good rough estimator for project costs that's a little more intuitive than the square footage alone. It's useful when you don't know the exact area because an area is strangely shaped like this giant cloud, or if you want to enclose an area like the safari farm and need to know how many linear feet you need to purchase. So symbolically we know the length times the width is equal to the area of a rectangle. In a square though, the length is equal to the width. So you can say that the length squared is equal to the area. Now if we want to find the size of any of those lengths when we know the area, all we have to do then is take the square root of the area. I like to visualize problems because it helps me see what's really going on. This graph is particularly rewarding because it shows just how many different length times width combinations are for a given rectangular area. I know it looks like a lot, but it's pretty straightforward. On the axes we have length in linear feet and width in linear feet. This is basically how far we can go in either direction given the area that we have, 75 square feet. The blue line represents the area for any given combination of length and width. The green box is the largest possible square that could fit under that line. This is literally the shape of the largest possible square given our area. Now I really like this graph because it's always interesting to see a nonlinear curve pop out of a linear problem like this. Further, we can think of the area under the curve as the solution space because it shows every possible combination of length and width equal to our desired area. When you look at the special case of either length or width equal to 1, you realize the other dimension must be the desired area. Think of a long, skinny 1 foot by 70 foot strip. What's surprising is the situations where one of the dimensions is less than 1, for example, 0.1 foot times 750 foot. And I apologize here for using decimal feet. In these cases, we see that the asymptotes, x is equal to 0 and y equals 0, emerge as we approach infinity. This is basically saying that if we went out on one of the axes, say length in linear feet, all the way out to infinity, eventually the width would have to equal 0. Given the infinite number of rectangular areas possible for any length times width combo, knowing how to find the maximum length square possible for a given area is a great rough estimator for whether or not your budget/inventory can provide enough material for a project. As for my deck, the estimate worked out well and I was able to paint my deck in time for the cat and I to enjoy it this summer. If you're interested in exploring the numbers for yourself, I've posted the MATLAB code I used to generate the graph on my GitHub and on my blog. Links are in the description below. Thanks for watching.